Leading AI models today can write a sonnet, draft a legal brief, and compose music. Systems trained on the vast library of human language have become remarkably fluent conversationalists. Yet for all their verbal dexterity, these LLMs are still strangely clumsy when it comes to the physical world. An AI can describe the physics of a falling object in perfect detail, but cannot reliably reason about what happens when a glass of milk is knocked off a table. It is book smart, but lacks street smarts. The struggle between being great at describing things and being good at real-world mechanics has become a frontier of AI research. Researchers think that models based only on language are hitting a wall, so the best AI labs like Google, Meta, OpenAI, and NVIDIA are pouring billions into an old idea that's making an amazing comeback. They are building world models. The core idea is that for an AI to graduate from a good talker to a good doer, it needs more than a library of words and images. It needs an internal sketch of how the world works, a kind of mental simulator that allows it to predict, plan, and act with a semblance of physical intuition. This is the quest to give machines a mind's eye. This show is an essential explainer of world models, the next frontier of the global AI race, using just everyday language. We go into the mechanics of what a world model is, how they work, and how they are distinct from your everyday LLM. We will track its journey from a long-time dream to today's tech race, dive into why it's making a big comeback, and show how tech giants are each making their own unique plays in their quest for superintelligence. At its heart, a world model is a mental simulator that lets an AI ask, "What if?" before it does anything. Humans use this ability constantly and subconsciously. A professional baseball player has only milliseconds to decide how to swing a bat, a period shorter than the time it takes for visual signals to be processed by the brain. They can hit a 100-mile-per-hour fastball because their brain instinctively runs a fast simulation predicting where the ball will be in the next fraction of a second. A world model aims to give a similar predictive ability to an AI. This simulator has three main moving parts. The first is seeing. When you walk into a room, you do not consciously register every pixel of light or the exact texture of the carpet. Your brain creates a compact, abstract summary of the scene, like the layout of the furniture and the people present. A world model's first job is to do the same, turning a flood of raw data from a camera or other sensors into a simplified, useful understanding of the environment. The second part is forecasting. Based on its compressed understanding of the world, the model predicts what will happen next. If the AI is controlling a robot arm and considers the action of pushing a block, the world model forecasts the likely next state of the scene. It predicts the block will slide across the table. This is the what-if engine. The third part is choosing. The AI uses its forecasting ability to test drive several possible actions in its imagination. It can play out a few steps of multiple futures, one where it pushes the block gently and another where it pushes it hard. It then scores these imagined outcomes based on a goal. For example, moving the block to a target location without knocking it over. The AI then chooses the action that leads to the best imagined future and executes that single action in the real world. The mathematics behind this process avoids trying to create a perfect atom-for-atom replica of reality. A perfect simulation would be far too slow to be useful for making quick decisions. Instead, the goal is to create a good enough sketch. The process involves two main ideas. First, the AI learns to compress the messy, high-resolution world into a simpler, abstract representation that captures only the important details. Second, it learns the rules of how that simple representation changes over time in response to actions. It's not so much about predicting every single pixel in the next video frame, but more about accurately predicting the important parts of the scene so it can make good choices. This creates an ongoing balancing act between how true the model is to reality and how fast it can make predictions, which is the major challenge researchers try to optimize. The idea of building an agent with an internal model of its environment is not new. For decades, researchers in fields like control theory and reinforcement learning have explored ways to give machines the ability to plan their actions by consulting a map or a set of rules about their world. But for most of this history, these models had to be carefully programmed by humans. Until now. The whole idea of AI world models really kicked off in 2018 thanks to a key paper called World Models by David Ha and Jürgen Schmidhuber. They demonstrated that an AI agent could learn a compressed model of a simple video game environment. The most striking part of their work was that the agent could then learn to play the game almost entirely inside its own simulated dream generated by this internal model. The agent became a competent player and could then transfer its skills to the actual game by practicing in its own imagination. This showed a path toward learning complex behaviors with far less real-world trial and error. A year later, Google's DeepMind division unveiled MuZero. Its predecessor, AlphaZero, had achieved superhuman performance in games like chess and Go, but it had a significant limitation. It had to be told the rules of the game in advance. MuZero took a major step forward by learning the rules on its own. It played games against itself, and through that experience, built its own internal model of what moves were allowed and what strategies led to winning. MuZero did not try to model the entire game board perfectly. It learned to focus only on the aspects of the game that were most important for planning its next move. This was a key development toward creating agents that could master new environments without needing a human-written instruction manual. This whole idea of learning a model and then training something within that model's imagination has been improved a lot by a bunch of different agents, especially the Dreamer family. These systems learn a world model from visual inputs and then use it to imagine thousands of possible future scenarios in parallel. By evaluating these imagined trajectories, the agent can learn successful behaviors for complex tasks much more quickly and efficiently than methods that rely purely on real-world experience. The most recent version, Dreamer v3, released in 2023, became the first algorithm to solve the difficult challenge of collecting diamonds in the popular game Minecraft without any human examples to guide it, a task that requires careful, long-term planning. Models have been steadily improving. Early systems required perfect human-supplied models of the world. The next generation of systems learned their own models, but did so within the structured, rule-based confines of games. The current wave of research aims to learn models directly from messy, unstructured video of the physical world, where no perfect rulebook exists. The sudden jump in excitement and money flowing into world models isn't just because of one big new idea. It's more like a bunch of cool things coming together that made this old dream actually work, and on a huge scale. First, the rise of video-native AI has been a primary catalyst. Generative video systems like OpenAI's Sora, trained on immense quantities of internet video, have developed a surprisingly robust physical common sense. These models show an intuitive feel for how objects should move, interact, and cast shadows, suggesting they are implicitly learning a model of the world's physics just by watching it. OpenAI has explicitly described its work on Sora as an effort to build world simulators. Second, researchers are now creating interactive simulators from video. It is one thing to watch a video of the world, it is another to be able to act within it. Google DeepMind's Genie family of models can take a single image or a line of text and generate a playable, action-controllable world. This technology could solve a major bottleneck in AI research by providing a nearly infinite source of varied and realistic training environments for AI agents to practice in. Third, there is growing robotics pressure. For robots to move beyond the factory floor and perform useful tasks in unpredictable human environments like homes and offices, they need to plan. World models offer a path toward giving robots the predictive foresight needed to tidy a room or assemble furniture. Then, the necessary compute and data are finally becoming available. Training a model on millions of hours of video or the continuous data stream from a fleet of robots requires enormous computational power and sophisticated data infrastructure. The hardware and software systems built out for the language model race, powered by thousands of specialized GPUs, are now being repurposed to tackle the even more demanding task of modeling the physical world. Finally, the limits of large language models have become clearer. While LLMs are masters of text and symbolic patterns, they are less reliable when it comes to consistent physical reasoning. They can describe a process, but they struggle to simulate it step by step without making logical errors. World models are specifically designed to fill this gap, focusing on the dynamics of how scenes evolve over time. These factors have created a powerful feedback loop. Better generative video models can create better training simulations for AI agents. The data collected by these agents as they act in the real world can then be used to train even more accurate and realistic world models. This self-improving cycle, where better simulators lead to smarter agents, which in turn provide better data to build even better simulators, is what the technology giants are betting on to accelerate progress toward more capable AI. So hopefully by now you are convinced of the power of world models. So the next question naturally becomes, how do they work? To see how these models work, think of them like a weather forecaster. A weather forecaster does more than just check today's weather and make a wild guess about tomorrow. A good weather forecaster would use complex computer models of the atmosphere to run multiple simulations. They input the current conditions, test different scenarios, and choose the most likely outcome as their forecast. An AI with a world model does something similar to decide its next action. Its process begins with seeing. The AI takes in raw data, typically a video feed. Instead of processing every pixel, it uses a component called an encoder to compress this information into a more manageable form. It identifies the important story beats of the scene, like the objects present, their relative positions, and their motion. This is like the forecaster creating a simplified map of current high and low pressure systems. Next comes forecasting. Given this compressed summary of the present and a potential action the AI could take, like a robot arm moving forward, the model predicts the following summary of the scene. It generates a forecast of the following story beat. This prediction is made by a part of the model, often a type of neural network called a transformer or a recurrent neural network, that is specialized in handling sequences of data over time. The final step is choosing. The AI uses its forecasting ability to play out several possible futures. It can roll forward a sequence of potential actions to see where they lead. It might simulate turning left, turning right, and going straight. It then compares these imagined outcomes to its goal. For a self-driving car, the goal might be to stay in its lane while avoiding obstacles. The AI picks the sequence of actions that leads to the most promising predicted future, and then performs the first action in that sequence. After that, the whole cycle begins again with a new observation. World models learn how things work by gobbling down all sorts of data. They gobble up tons of unlabeled internet videos to figure out how stuff generally moves and interacts. They also watch humans operating robots to see exactly how certain actions create specific results. Video game footage is another great teacher, showing them how to achieve goals. Plus, they're increasingly trained on fake data from computer simulators and even other AIs, like Google's Genie. Getting hold of this training data is becoming a source of competitive advantage. While there are tons of internet videos out there, getting good quality data from actual robots is tough and pricey. Companies with a bunch of robots, self-driving cars, or those that can build their own simulators have a real advantage. This gives them an edge that's super hard for others to catch up to. There are several fundamental reasons why the world model approach is considered so promising for building more capable AI. It is much more efficient to learn a single reusable physics sense than it is to learn every new task from scratch. An AI that has a general model of how objects fall and collide does not need to be shown thousands of examples of every possible object to learn how to handle them. The second is the ability to perform reasoning over long horizons. The capacity to think ahead is essential for solving any complex, multi-step problem. A purely reactive agent can only respond to its immediate surroundings. An agent with a world model can simulate the consequences of its actions far into the future. This would let it formulate and execute intricate plans. The third advantage is generalization. An internal sketch of how the world works should be transferable to new situations. A human's intuitive understanding of physics allows them to navigate an unfamiliar kitchen or drive a rental car. Similarly, a well-trained world model should allow an AI to apply its knowledge to new tasks and environments it has never encountered before. An agent trained in a simulated warehouse should be able to transfer some of its skills to a real warehouse, even if the layout is different. Despite the excitement and rapid progress, building a truly capable world model is not easy. One of the most fundamental challenges is the trade-off between fidelity and speed. A highly detailed and realistic simulation of the world is computationally very expensive, making it too slow for the real-time decision-making required by a robot or self-driving car. A faster, more abstract simulation might run quickly, but could miss crucial physical details or edge cases, leading an agent to make a catastrophic mistake in the real world. Finding the right balance is the most fundamental area of research for world models. Another tough nut to crack is causality and common sense. Predicting the next pixels in a video is not the same as understanding the cause and effect relationships that govern the scene. A model might learn that a thrown ball is correlated with the ball moving through the air, but it may not understand that the force from the throw causes the motion. This lack of causal understanding can make models brittle. They can fail in surprising ways when faced with a situation that violates the statistical patterns they have learned. For robotics, the biggest hurdle is often the reality gap. The messy and unpredictable nature of the real world with its variable lighting, friction, and sensor noise can easily confuse an agent trained in a sanitized simulation. Bridging this sim-to-real gap is a major focus of robotics research. New concerns pop up about how these powerful world models and the agents trained in them could be unsafe or misused. How do we stop an agent from finding sneaky ways to cheat in its fake world to reach its goals, especially if it's not safe? And how do we keep these tools from being used to make super convincing fake news or to teach self-driving systems to do bad things? We'll need to invent new ways to test for safety and new rules for using them responsibly. You might have started to see that the world models and large language models, like the ones behind ChatGPT, are pretty different. They're both trying to achieve intelligence, but they go about it in unique, though possibly complementary ways. Large language models are like super smart word wizards. They gobble up tons of text and get really good at guessing what word comes next. Their smarts come from how words relate to each other statistically. This makes them awesome at language, logic, and abstract stuff. World models, on the other hand, are like keen observers of the real world. Their knowledge is all about how space, time, and physical interactions work. The most likely future for advanced AI is a synthesis of them into a unified agent. This agent stack would function like a complete cognitive system with different components handling different tasks. The language model could act as the verbal brain, responsible for high-level reasoning, understanding complex human instructions, and breaking down large goals into a series of smaller, manageable steps. For example, it could take the command "clean the kitchen" and generate a plan like, first find the sponge, second wet the sponge, third wipe the counter. The world model would then act as the motor cortex or mind's eye. It would take these smaller steps from the language model and translate them into physical actions. It would use its sensors to see the current state of the kitchen, use its internal simulator to predict the physical consequences of its actions, and execute the plan step by step. A physical robot or a set of software tools would serve as the body, carrying out the commands. The tech giants bet. Big tech is in a heated arms race over world models. Google DeepMind is going all in on generative interactive environments. Their Genie 3 model is aiming to create endless, controllable, and consistent virtual worlds just from simple text prompts. These worlds will run in real time, letting an AI agent explore and learn within them. OpenAI, the company behind ChatGPT and the image generator DALL-E, is betting on scaling up video generation as a form of simulation. With its model, Sora, OpenAI's approach is to train an enormous model on a vast and diverse data set of internet videos. The belief is that if the model is big enough and the data is rich enough, a general-purpose simulator of the physical world will emerge from the pattern. Meta, led by its chief AI scientist Yann LeCun, is taking a different route. Their model focuses on predicting the outcomes of actions in a simplified, abstract way, rather than trying to generate super-realistic video. The idea is that it's more efficient for an AI to grasp how the world works without getting bogged down in creating perfect visual details. NVIDIA is positioning itself as the foundational infrastructure provider for this new era of physical AI. NVIDIA is pushing its Omniverse platform to make super-accurate digital copies of real-world stuff, and its Cosmos software to create world foundation models. Basically, they're building the tech, both physical and software, that lets other companies create, teach, and use their own systems that interact with the physical world. Neck to neck with these tech giants are startups like UK-based Wave, which has built GAIA, a world model specifically for self-driving cars. It learns to predict how tricky traffic situations will unfold, helping a self-driving car guess what other drivers and pedestrians will do so it can make safer choices. Though fully capable AI agents are still a ways off, the tech is set to pop up in more specific uses pretty soon. First, robots and home assistants are going to get way smarter. Imagine robots that can actually sort your laundry or clear the dinner table without a hitch. That's because world models help them figure out how to interact with all sorts of stuff in your messy house. Then there's self-driving cars. We're talking safer and more reliable rides because these models can predict what other cars and people are going to do. Companies like Wave are using them so vehicles can practice how to react to crazy, dangerous situations in a virtual world. And creative tools and games are going to be transformed. Google's Genie already shows how world models can whip up entire interactive game worlds from just a simple text prompt or a sketch. This could seriously cut down the cost and hassle of making games, opening up a whole new world of entertainment. Making AI understand how the world works is a big milestone in the race for superintelligence, a state when AI surpasses the best human brains in practically every domain of interest. The goal is to turn AIs from just watching to actively solving problems. Top tech companies are betting that if machines can get a good grasp of how things usually happen, it'll bridge the gap between the chatbots we have today and the smart, helpful AI partners of tomorrow that can work safely and effectively with us in the real world.